Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, let's dive right into rocket engine parts. So let's dive right into it. Now, you have to understand this aspect. I have covered many of these parts in detail in dedicated video. However, this video is intended more as an overview, so you get an idea like how they work with each other. Because again, it's a system, it's a complete ecosystem of powers and pressure. So we have to understand it as a whole. Now, what does a rocket engine inherently does? Like what his job is? His job is to turn chemical energy into usable thrust. That's the whole point. You have chemical energy, it's trapped into your propellant. You extract it, you convert it into usable thrust. Now, how does rocket engine work fundamentally? Like that's the part. What's it doing? How it's doing that is using propellant as a reaction mass. Basically, it's throwing stuff and then getting pushed back as a recoil. However, there are two vectors to that. Vector number one is the velocity of things that you are throwing. Basically, if let's say you have 1 kilogram of mass and you're throwing it, okay, that's one vector. You need to know another aspect also, which is how fast you're throwing it. You know kilogram, what is the meter per second. If you have these two data, then you can extract how much push you're gonna get out of it. Without that reaction mass, this does not work. That's why a rocket has such a large fuel tanks. They need that to push down, and that's why like they have such a huge flow rate where they are like pushing. You will always hear things like they are draining swimming pools per second. That kind of power you need to do that, because literally you are pushing it off the earth has very deep gravitational well, 9.8 meter per second squared. So that's why you need a lot of reaction mass. Now again, those two things are interchangeable, meaning if you have throwing something that is very light but you can throw it at ludicrously high speed, you can get the same performance if you are throwing something that is like very heavy but slower speed. So those are the two things, and those create your reaction mass. You have to throw something away. And generally for space missions, I'm not talking about military missiles and all that, just generally for space missions, we always select two-part components, and which components will be used, basically which propellant mix would be used, that is dependent on the mission. For example, if you are designing Saturn V, you will have different requirements for the boost stage versus your third stage, which is supposed to take stuff to the moon. There are different requirements for that, so you will choose your propellant mix based on that. And liquid fuel with liquid oxidizer, generally liquid fuel could be many things. There are right now one new contender that is coming up, that is liquid methane, CH4. Before that, RP1 was the king. Falcon 9 still runs on that, and there are some other options which are not as popular, but you get that point. Like RP1 is like it has the most oomph to it. Basically, if you want to get out of a gravity well, this has the most amount of horsepower, but again, it's heavy byproducts, meaning once you combust them, the products are heavy. Inherently, it cannot go very fast. So it's really good if you do not need too much velocity, but you need a lot of thrust, so to say, first stage. But if you are in upper stages and you are like I really need to throw things really far out, you will see people are always choosing things that have hydrogen in their upper stage, because that allows you to get higher velocity. That does not have much that oomph, but does have velocity. So you use the stage once to get it off the ground, and you use hydrogen upper stage to send it very far away. Or you can use methane, which is like good enough compromise between RP1 and hydrogen, where it's like it gets the both part done. And it's all about balance. Balance is the critical aspect of it. There never is nor ever will be an engine that is like I got this all. That physics does not allow that. Physics flat out, nah man, you can't do that. So you always have to balance cost, because again, if you can't build it, what's the point? Power, you're not gonna put a giant F1 main engine as like emergency escape engines. Every engine has a certain requirement. Again, you may require engines that are a bit more finessable, meaning if you want to boost International Space Station, you don't want an engine to go like you don't want that. You want like gentle, controllable thrust. In those sort of scenario, power requirement would be different. You may want control, meaning how do you want to start the engine? How do you want to restart it? Do you need to restart it, or you just like light it on the ground and just YOLO it? Or you want like, hey, for upper stage, specifically for upper stage, you want to reignite it so you can circularize the orbit, or make it more elliptical so it gets like to higher elevation. So you have to choose that also, control aspect, how much. And then you have lifespan. Now lifespan is a very new concept, because before this, only engine that was truly reused again and again, that was RS-25 from Space Shuttle. Almost nothing else was truly reused. And right now Merlin is the next big thing, and Merlin is using kerosene, so it's inherently very gummy kind of things. And again, it has such a long hydrocarbon, meaning kerosene has very long hydrocarbon, and if you are burning them, many times it has the side effect of becoming polymer, plastic things, meaning it can gunk up your stuff. very badly. So inherently there is a lifespan limit. They have to keep the cleaning the engine, they have to keep cleaning the turbines. So they are like generally after 10 times they are like just throw away the engine. It's just not worth cleaning it again. And again, it also has some other side effects of that. So if they wanted to build Mark II engines, which is a rafter, they are like, you know what, thou shall not use something that gunks up the everything. Thou shall use cleaner fuel, which is methane. Methane has again, it has only one carbon, so it cannot create like long polymer chains. So it's very good. So lifespan is also becoming a critical aspect of it. So all these four things have to balance each other out, and perfect balance is one where you're like, this is what I want to do, this is how I want to achieve it, and this is my budget. If it all matches up, you have amazing thing. It does not matter Russia built the most amazing engine. It's like, yeah, they never went to the moon. What's the point? Like F1 engine, was that good? Yeah, it was amazing because it had one job and it did it so goddamn well. It's taking us 60 years to redo it. So yeah, that's the whole point. So let's start with the heart of the pump, that is turbo pumps. Now, turbo pumps are the core aspect of it, meaning if you take oxidizer, you take fuel, you burn that, all you have is a goddamn flamethrower. It's not a rocket, because I specified you need two vectors. You have nothing at that point. You just have hot gases that are coming out, which are not not enough mass is there, B, not enough velocity is there. So it's like nothing is going to happen with that. So you need turbo pump to increase the mass flow into the combustion chamber. Now this puppy is responsible for that, or turbo pumps like that design. Now turbo pumps require lot of energy, like a lot kind of energy, meaning think of turbo pumps as the same way as you think of turbocharger. Turbocharger does consume a lot of energy from exhaust. Again, because it's working on exhaust, you do not think too much about it. It's not a parasitic loss, but it does take a lot of energy. You will, unless you are dealing in eBay where they're like, this 5 watt motor is like, turbocharging your car. Yeah, that's not happening. Turbocharger does require a lot of horsepower. Ask F1 team, like they literally a 50 horsepower motor just to drive that. It takes a lot of energy. This is same here. So how much energy we are talking about? Well, megawatts. We are talking about megawatts, meaning you can literally have something that's like 50 megawatt, 60 megawatt, or even 100 megawatt. So that kind of energy level we are talking about. And the bigger you make the engine, the more energy this will take. So if you're talking about something small, let's say from Rocket Lab Electron rocket, Rutherford engine is small, this puppy. Now it does not need too much horsepower. It only needs 50 horsepower. Now if you're not familiar with how much is 50 horsepower, think of it this way. Your average basic bitch car is 50 horsepower. A car versus this tiny engine. Let that sink in. So that's why, like, it consumes insane amount of energy. So there is an upper limit, like basically unless you can make the pump as big as you want to, you can't really flow a very large engine. Now it does need a rocket to drive this, because again, where the heck you gonna get like freaking 20 megawatts? So you can, again, for small one, Rutherford does try batteries, but again, thankfully it only has to work for 2 hours, and the power requirement is low enough where it's like modern lithium ion can touch it. But the moment you go any bigger than that, yeah, no, thou shall say no to it. And that's why even the Rocket Lab themselves, they are working on Archimedes engine, which does not have battery system. It has turbo pumps running on gas generators. Now gas generators are basically small cold rocket. What does cold rocket mean? Cold rocket simply means whenever you are burning fuel and you're controlling the both aspects, fuel and oxidizer, you can achieve what we call stoichiometric ratio, meaning you're getting perfect burn. Now problem with perfect burn is it's almost 3000 degrees Celsius, meaning there is nothing that can withstand it, like nothing. The only reason jet engine turbine blades do not melt is simply because they are surrounded by atmosphere, meaning there is nitrogen, like the compressor stage is flooding nitrogen there. So inherently there is a buffer stage of nitrogen itself. When you're talking about rocket engine, it's just oxygen, man. It's just oxygen and fuel. So if you really want to achieve high temperature, it's like, I got this, man. I'm gonna give you 3500 degrees Celsius, like ludicrous, something like that. And there is no metal that's like, yeah, no. So how do you cool it? Well, you have two options. A, you burn it in completely, whether you choke one or the another, or you can overflow it. Basically, you can have a scenario where it's like, I'm gonna send this much X amount of methane. I'm gonna send X plus 30% oxygen. Now that will be classified as oxygen rich, but because the other oxygen is acting as a buffer, because again, you release the chemical energy, magically other oxygen will not react to it unless it's reacting with the chamber walls. It has no other energy, so it's just gonna act as a coolant. So at that point in time, so that cold rocket will drive the turbine without melting it. Thankfully, it will have still enough oomph to drive like multi-megawatt equipments. At that point in time, your rocket is good to go. And what do you overflow it with? That's up to you. If you are seeing sooty outcome generally, and if it's a rocket engine running on kerosene, generally they are overflowing the kerosene side of things. Now, why don't they overflow oxygen? Well, oxygen is reactive, and when it's hot under pressure, it has the tendency to make love to the metal. So unless you want your metal to disintegrate, you do not want to do that, or you have to develop really complex metal alloy that can handle that kind of stress. So that's how you achieve that. That's how you drive the turbine drives the main pumps are generally sized based on what you want to drive, because if you have hydrogen driving, you need huge pump, because again, hydrogen is very low density. Ideally, you want something that has, like, same in both of the components, meaning oxidizer and fuel should be more or less the same, so same turbine design can be used in both of them. Generally, we are not that lucky, but you get the point. And again, because if you factor in overflow, the engine design becomes a bit more complicated. And this is the 90% cost of the rocket. That's how important this is. Then we come to injectors. Now, injectors is the department that makes your rocket burn, meaning it allows you to properly mix fuel and oxidizer. To give you a context of it, if you have liquid oxygen, if you have liquid methane, and you just put them into a beaker, nothing's gonna happen, like literally nothing. And you might what if I set a match there? Something might happen. Yes, why the heck there is something? Because it's too goddamn cold. To burn it properly, you may need to achieve what we call flash point. Basically, it should be boiled, it should be atomized. And again, in heavier fuel, it has to be atomized. Basically, if you send a stream of basically RP1 and you try to light it, it's not gonna burn. It's like, no, I don't give a damn, I'm not gonna burn. Unless you have a very high temperature blowtorch. So what do? We atomize it. Basically, we make it into small mist. At the moment you make it into mist, then it's like, I got this. Basically, you have to increase the surface area. And same goes with when you are talking about basically very cold hydrogen and very cold oxygen. You may think it's just touching it, but you need three things for proper successful ignition. You need fuel, you need oxidizer, and you need temperature. So whenever Merlin was developed, Merlin in Falcon 9, they had an issue with like, how the heck you ignite it? Russian designs literally have a matchstick up their ass to light it on fire. That's awesome, that does work, but again, it does not have the ability to restart. How the heck you restart the engine if you you need something and you are landing? How the heck you're gonna go set a match up its ass? You can't. So what they come up with the idea, basically third component, T-tap. Now this component has this interesting effect where if it touches oxygen, it inherently self-ignites. So what they do is and that ignites at very high temperature. So meaning if there is kerosene nearby, it's gonna burn without any issue. So they flush a little bit of T-tap, little bit of oxygen, kerosene, poof, rocket go. And that's what the green flame is. So that's the job of the injector, basically mixing these things. If you, again, fire will never touch this part, it will always burn here. And there's another aspect, fire should not touch this. Now you're like, wait a minute, this is inside a rocket engine, how the heck fire does not touch this? That's the whole point, that's the whole thing. This is also a design criteria. Whenever you are flowing propellant, you have to design in such a way that it does not touch, or you may design it in such a way that it touches it but it can handle it. But generally prefer is yeah, we shall not touch here. So you will have swirl injector. The injector will be designed in such a way that it may create enough smooth flow, and turbulent here, turbulent, perfect burn. Smooth flow, it will not burn. So this acts as a buffer zone. Same happens in jet engine also. When you have jet engine and they have flame trench kind of scenario where the fuel injector is going into the flame holder, and it's designed in such a way that flow rate is high enough where flame cannot touch this part. If it touches, it will melt, it will block itself. So, and boom, happens. So that's why you have to design in such a way. This is very complicated issue, and there are many options. Now you have shower head, which if you are like, wait a minute, that sounds like shower head. Yeah, it is shower head. People have tried to actually make rocket engines out of actual showers, and it has actually worked. Again, not the most efficient system, because this puppy defines your combustion efficiency. Meaning if this part is happening properly, if you are properly atomizing your fuel, if you are properly mixing them together, and its combustion flow rate is stable enough, then you're gonna get good effect. In that sort of scenario, you can achieve almost 98% combustion efficiency. Realistically, it's unlikely that you ever gonna achieve 100% stoichiometric ratio, but 98% is good enough. So that's how you do it. You have shower head, then you have pintle. Pintle is used in Falcon 9, and then you have swirling injector. They are now becoming the next big thing. This sort of design, basically they flood it with oxidizer. Then from other side, from let's say one thing is going clockwise, another thing will be going counterclockwise, and it's gonna create two cones. These two cones will intersect with each other, get atomized, and voila, you have your injector. Now it also allows you to cool your engine. Wait a minute, this is pumping fuel and oxidizer. How the heck it can cool the system? Again, some designs, not all designs, some designs you have the luxury of designing the flow in such a way that overflowing part, generally there is always something that is overflowed, because you don't want temperature, you want mass flow. So you will use the lighter element, basically whichever the lighter is. Either oxidizer is lighter, you're gonna send extra oxygen. If fuel is lighter, you're gonna send extra fuel. That way you can absorb the heat and turn it into mass flow. and the same effect is achieved by basically our jet engines by using nitrogen from the atmosphere. So in those sort of scenario, you can literally have the central part is burning GG. The outer part you can have a scenario where it's like slightly fuel rich if it's a fuel rich system, or slightly oxidizer rich if it's an oxidizer. So you get perfect stoichiometric in the center part, and the outer part is basically protected by a warm curtain of, let's say, if the core is 3000 degrees Celsius, the outer side would be around 2000 degrees Celsius. And for rocket engine point of view, that's cold enough. Again, that's how like a jet engine is also cooled. It's like you have jet engine and it's cooled by 700 degrees Celsius air. Yeah, 700 degrees Celsius cool if your hot side is 1500 degrees Celsius. Same happens here. So you can design it this way, and this defines your specific impulse and everything, because this is the part where chemical energy is being liberated. Now, where this liberation happens in combustion chamber. Now, this puppy takes chemical energy into thermal energy. Right now, you do not have thrust, you just have thermal energy. And this is the hottest part in the engine. Meaning, if you take the whole engine, you may see the, the looking part, the hot part. Nah, this is not hot. Chamber is the hot part. So, this is the hot part. And everything melts here. Basically, there is nothing you can build this puppy out of which will not melt. Now, I'm like, wait a minute. If it does not melt, if it's supposed to melt, how the heck we have rockets that works? Well, reality is you have to actively cool it, meaning it will try to melt and you try to like, hey, that shall not melt. So you have to either actively cool it. Basically, in case of F1 engine, the Granddaddy moon rocket engine, they literally had kerosene running in there. Now you're like, why the heck they were running kerosene? Again, they were not planning this to reuse this engine. So you can, if your turbopump have enough horsepower, you can literally flush kerosene here, and you will not have any issue of like gunking up. Again, even if it gunks up, you can just force it through. So that's how you're gonna achieve that. And again, pouring liquid oxygen there, that may sound awesome because again it's cold, that's awesome, but problem is it's reactive. Kerosene is not reactive, so that's why like you want to flood it with a basically fuel. Same is done in RS-25 space shuttle engines. They are using hydrogen. Hydrogen is not reactive. Again, inherently not reactive as oxygen. Oxygen puts way too much stress on metal. So they are like generally prefer not to flood it with oxygen. And in case of Raptor, they are using methane to flood it, which is generally you rarely will hear in it. Again, it can be done. It's just like if you have metallurgy that is strong enough, you can do it. Generally, they prefer to just fuel cool it. That's one way of cooling it. Better way of cooling it. But there is a cheaper way, that is ablative cooling, meaning you will put something there that will burn off, and you will like, doesn't that sound counterintuitive? Well, yes, it burns off, it changes your geometry while in flight, but does have the benefit that it's taking heat away. Meaning if you have your chamber wall, this shall not melt, you put a graphite layer, very thick graphite layer. Now graphite burns, but again, if it's burning, it's outgassing, it's like literally going away, so your heat is not penetrating through it, because again, the thing that's supposed to absorb the heat getting destroyed by it and getting exhausted, you don't have to worry about it. Again, it's supposed to last for around 2 to 3 minutes. That's how many cheap rockets engines are made. Or Merlin, when it was used in Falcon 1, they did not have the money to engineer absorption active cooling, so they were using ablative cooling. Ablative cooling is also used by missiles because again it's cheap enough. So many times you have to do one of these things. Either you make it active or you make it adaptive cooling to survive. Now pressure and thermal here at this point in time is idiotically high, meaning one of the most extreme places ever. Like in entirety of engineering world, this is one of the places that you'd never want to put anything in. It's very hot, very high pressure, very brutal. Now, this is the another reason why you do not see huge engines like this F1. And by many design elements, F1 may have been the largest engine we would have. Again, we can make something more powerful than this, but like this one, RD170. Now, it is more powerful than this puppy, but again, they could not figure out how to stabilize it. They could not figure out how to cool it. They're like, you know what, just have one giant turbo pump and 4 nozzles. Because it was just too goddamn difficult to have like giant combustion chamber that is stable enough, that does not melt, all that figures, like just have 4 small. So that should give you a context of it. Like that's why this is like the biggest engine there, and it's very unlikely that we ever gonna surpass it. So that's the combustion chamber aspect of it. Then we come to the nozzle aspect of it, because right now all you have is thermal energy. Now how do you take thermal energy and make it into thrust? You basically convert it. Now what you have right now is a lot of high temperature and you have a lot of high pressure. So basically you send it through a transformer. Now that transformer is in business is called converging diverging nozzle. Basically you converge this puppy, choke it, and then you expand it. Converging, diverging. Now this is acting as a transformer. So you cannot create free energy. So you generally trade temperature and pressure and you get velocity at the other end, because I specified it. Again, the mass will not change. Again, mass, if let's say you are sending 50 tons here, the exhaust will still would be 50 tons. Only difference is you are changing the velocity. Now to change the velocity, you have to give up something. So what you are giving up is temperature and pressure. So what's happening is you're pouring propellant there. Propellant is burning. It's getting insanely hot. Now hot things wants to go somewhere. It's like, it's very high pressure. It wants to go. It goes here, but again you are choking it. You are like, no, you will not go here. Again it tries to, like your turbo pump is still pushing it through. Now it still moves it. The moment it moves from this throat, it finds free space. It's like, I am free. So what happens? It gets higher velocity. Basically now it goes into lower in pressure, lower in temperature, but it gains. Again, you cannot just like give these things away and like have no repercussion is you will barely have subsonic here, you will have supersonic to hypersonic on the other end. Like you can easily achieve Mach 2 or Mach 3. So that's the whole point. This is the transformer that allows you to convert thermal energy into thrust. And if you ever noticed marked diamonds, you're like, why the heck there is marked diamond? Well, because atmosphere is pressing it. That should give you a context, like how much pressure we have here. Like if you hear about Raptor engines, you're like, 300 bars. And you're like, wait a minute, atmosphere is 1 bar. Then why the heck we are getting shock diamonds? Because the velocity has increased so much, it has compromised the pressure aspect of it. It's no longer high pressure. So atmosphere is like, I will compress you. So basically you have gas, atmosphere compresses, but when you compress it, you end up gaining the pressure. So it fights back. It's like, fight back. So it fights back. Then again it cools off. Fight back, cools off. Fight back, cools off. Fight back, cools off. And atmosphere wins at the other end. And that's why if you ever watched any Falcon 1, I'm saying F1 engines are running in Saturn V launch from, and they have very good tracking images. You should check that on YouTube. You will find that like, when as they are going, you're seeing shock diamonds, amazing, good looking shock diamonds. Again, it's very dirty, but it's like you can pay attention to it, you will notice shock diamonds. The moment it starts to go upper atmosphere, these shock diamonds disappear. And once you go to like, 60,000 feet and 70,000 feet, it's like, yeah, no. And then you have to worry about what we call expansion ratio, basically this throat to expansion. Now this has to be designed based on needs, what your engine needs to do. For example, if your engine is supposed to work as a stage 1 and it's not supposed to go to absolute raw vacuum, it has to start in sea level, this ratio won't be too high. The reason for that is atmosphere is there. Same way atmosphere can compress it here. Worst case scenario, it can compress it inside the nozzle. That could create what we call flow separation, meaning your hot gases can be separated from J1. That could create very severe oscillation, meaning again, this is like, things are happening. You will never have a stable flow. That physics does not allow that. There is like chaos there, inherent chaos there. So in that sort of scenario, you can literally have oscillations. Those oscillations could get so brutal, it could destroy your engine. So in those sort of scenarios, generally flow separation is not something that you want to have ever. So in that sort of reason, you have to design it. You have to design, hey, I get it if I make it like, a low expansion ratio, it's very bad for the efficiency. It's not amazing, but it will survive takeoff. So at the second stage, you make it as expansive as possible, the larger diameter as possible, so you get more oomph out of it in vacuum. And that's why you will notice that Falcon 9, you in the same diameter, basically you take the same core diameter, the core has 9 engine, and the upper stage has only 1 engine which has giant nozzle. The giant nozzle is there because again, stage 1 it pushes the stage 2 so far up there, and there is no atmosphere for that point in time. Again, it even teaches the basically fairing. So that should give you the context. That's why like generally want to make it as large as possible to optimize basically, basically selling off your temperature, selling off your pressure to gain the velocity. The higher the velocity, the further you can go. So that's the part of nozzle. So this was my presentation where I wanted to give you an overall holistic view of this rocket engine. Hopefully you have liked it, learned from it. In that case, please give the like button, share it amongst your friends. That will help me a lot. If you didn't like it and didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.